All right, so today we're formally jumping full bore into Chapter 5, Circuits with Memory. And what I had started with, just as a review here, let's do that. I had shown you that if we hook up two inverters together, some kind of a logic generator circuit here, we called our output Q, what we would have is a stable configuration. If I had low here, that would mean coming out of this inverter, I would have high here, which means coming out of this inverter, I would have low. And that low would propagate back to the input. So everything was happy. There would be no change, even though my logic source was disconnected. And let's just briefly look at that again for a moment here. Let's go back to the inverter latch. Oh, save changes. Inverter latch. There it is. Make it big. Everybody can see that? So right now where the switch is closed, you can actually see that one of the lights is on. If I remove that switch, the light stays on, okay? Because the output reinforces the inputs over and over again. If I close the switch and force it to a different state, we see that it still maintains its state. This is a stable configuration. I was thinking about this over the weekend, and I thought, you know, it'd be really cool to show an astable configuration. And this is what I had here. So this is my astable configuration up at the top. All right, 3 inverters. And it actually, if I try to simulate this says it cannot find a solution. It's basically lost its cookies and gone home. So what I'm going to do is I'm going to force it to start at a high. And now if I try to simulate this, now it will actually simulate. And when I remove the source, we actually see it in its astable configuration. Notice the light is constantly changing. If you were to look at these high and low signals, you would see that there was a small propagation delay between triggers. If you actually look at the currents through these devices, you'll see that the current through each device spikes a little bit after the other. And the blue is actually in the opposite direction. The blue is the one in the middle, I believe, if I stop this. Well, it doesn't show me the colors anymore. But if I go back to, oh, the blue is opposite there. So you see that each one of those has its own spike indicating high or low. So it's an astable configuration, which we want to avoid because that's bad. Okay, so that's our basic memory circuit. We moved on, okay, to the idea that a NOR gate with some logic input. Remember the rules for NOR. I'm having trouble remembering NOR. There we go. 1, 0, 0, 1. Effectively, if you put a 1 in, it sets everything to 0. If you put a 0 in, it's an inverter. 0 becomes 1, 1 becomes 0. So if I were to do this, that is equivalent to an inverter. So we augmented this by saying, all right, let's assume now that we have our logic input here going into a NOR gate, going into another NOR gate, and back around. This is the same circuit. Everybody remember so far? Okay, the only thing we did that makes this a little bit more interesting is we changed the orientation of these gates. We created a cross-coupled set of NOR gates. So instead of them following each other linearly left from right, they're above one another. Okay, so we said that's ground, and that's ground. And we named these inputs and outputs. We called this guy Q, we called this guy Q bar, we called this guy S, and this guy R. And what I said was, all right, let's look at what we can have for S and R inputs and what will happen to Q and Q bar. And what I'm going to do is I'm going to have one more row on this table called state, because at this point, once we start entering into circuits with memory, state is a much more useful descriptor than a truth table. So let's just review that real quick. If I put a 1 on S and a 0 on R, and I'll annotate over here, nor truth table. If we have a 1 on an input, it doesn't matter what the other input is, we just get out a 0. Otherwise, it acts like an inverter. So where we have a 1 here, we automatically know that it's 0. We don't even have to look, we don't even have to look at this output. Now that we know that, we can look over here. Before we had calculated this output, we could not determine the output Q. We couldn't determine the output Q because we didn't know what the other input is. When you put a 0 into a NOR gate, it inverts the other input. And we didn't know what it was. However, now we do. We know that it is a 0. And 0 NOR 0 is a 1. Now again, that 1 is going to propagate over here, but it doesn't change anything. 1 NOR 1 is the same as 1 NOR 0. So this is a stable configuration. We get a 1 on Q, a 0 on Q bar. This is what's known as the set state. All right. If at this point we were to change this 1 to a 0, what would happen? Well, right now we know that this is a 1, 0, so we invert. Anytime we see a 1, we invert the other input. So this becomes a 1. That 1 comes over here. 1 NOR 0. I'm very sorry. Give me a minute. Hello. Yes, I'm actually teaching right now, but my fiance is at the house by any time. Thank you very much. I'm very sorry. My gas company is to come 3 times trying to inspect, and if you don't pick up that call, they bump you 3 months. I apologize. Set state. We have changed the S input to a 0 and the R input to a 0. And what we end up with now is this 1 propagates over. 1 NOR 0 is a 0, which propagates through again. And this becomes a 0. Now 0 NOR 0 is still a 1. That 1 propagates over. 1 NOR 0 is now still a 0. By the way, I should mention that now that this is an S input, it's not tied to ground anymore. It's an actual logical input. Okay. So now what we have is the same output. We put a 0, 0 in here, and we retain our 1, 0. This is what's known as a hold state for reasons you'll see in just a second. So I'm going through all the combinations not in binary order, but in the way that makes sense for transitions between states. So let's clear this out. Okay. The only thing we know right now is that we currently have a state of Q being 1. If I now change this to a 0 on set and a 1 on reset, we go through this again. All right. We know that anything NORed with a 1 is going to be a 0. Which is not really what I would have expected. Oh, yes, it is. It's going to be a 0. That 0 propagates over. 0 nor 0 is a 1. The 1 comes across. 1 nor 1. What is 1 nor 1? It's a 0. So again, we're in a stable configuration here. So now when I put a 0 nor 1, I've swapped my outputs. Q bar is 1, Q is 0. We call that a reset state because we've reset Q. Reset tends to mean go to 0. All right. Now, in the past, we've dealt with truth tables. You put something in, you get the same thing out every time. Doesn't matter if you do it today, tomorrow, the next day. We always get that. If I change this now back to 0, 0, okay, what we're going to see is we have 0 nor 0, which is a 1. So the 1 stays. That 1 propagates over. 0 nor 1 is still a 0. So it stays. So now, when I put 0, 0 in here, I get a 0, 1. So these two things are directly in conflict, right? We put in a 0, 0. First time we got 1, 0. Second time we got 0, 1. It has to do with the order. 0 is the hold state. Okay? The only reason that works is because previous to putting in the hold state, we had a set or a reset state. And I have shown, I think, in the demo over here what happens. Oh, let's turn this back on here. Looking at only the bottom circuit here, this is our cross-coupled NOR gate. And we can look at this. Right now, when we turned it on, it eventually settled into a particular state. 0, 0 is the hold state. When I turn on this output, okay, what is 1 nor 1? That's a 0. So I see a blue line coming out. 0 nor 0 is a 1. Okay. So everything is stable in this configuration. If I go back to 0, everything stays the same. If I turn this one on, this is my set state, so it applies and turns that on. Turns on Q. So Q and set are diagonal to one another. R and Q bar are diagonal to one another. To make this next one work, okay, the one state I haven't done is both on. If I have 1 on, I know that 1 NORed with anything is always 0. So I do see a 0 out here. 1 NORed with anything is a 0. So I see 0 out here. This is what's known as the forbidden state. Let me just write that down. Okay. 1, 1 actually gives you a Q and a Q bar of 0, 0. And that's called forbidden. And it's called forbidden for the following reason. I'm going to pause the simulation so that everything happens at exactly the same time, because that's the only way this works. I'm going to set both of these back to 0, 0. So I'm going directly from 1, 1 to 0, 0, the forbidden state. And if I hit run, for just a moment, there was a problem. Let me do it one more time. Turn that back on. How do I get rid of this? Stop looking at this for a moment. Go away. Go away. Go away. Okay. So there I am. Toggle this, toggle that, and hit run. Eventually, it turned on one of the lamps. But before that, it was having a bit of a problem. It was in a very fast astable state, which is exactly what happens up here when I disconnect things. This is astable, and I've got this running very slowly in terms of simulation time. If I speed up that simulation time, you see that it's a little bit more frantic as to what's going on, oscillating back and forth in an astable state. So when you go from a forbidden state back to 0, 0, you end up with an oscillation, an astable state. And again, that's because you went from 1, 1 to 1, 0. So that was a review from last week as to what we talked about. Going ahead from here, we said, what happens if we do the same thing with NAND gates? All right. Now with NAND gates, things are a little bit more interesting. We're still going to have those same states. States that I'm referring to are set, reset, hold, and astable. The difference is, okay, let's see here. We typically will call this S bar and this R bar. And here we'll have Q and R. So this latch is typically referred to as an S bar R bar latch, whereas this latch is just called an SR latch. Okay, so an S bar R bar latch, you might be able to see what's going on here. SR Q bar. I don't know why I wrote R there. That was supposed to be a Q bar. Trying to go too fast here. Q bar. So here we go. Let's start by putting us in a known state. I'm going to put a 0, 1 in here, and let's see what happens. 0, 1, and I need my NAND gate table. All right, a NAND is not AND. 1, 1, 1, 0. So effectively, if we have a 0 input, we know that we're going to have a 1 output. If we have a 1, we're going to see an inverter. So where I see a 0 here, I automatically know that my output will be 1. Doesn't matter what my current state is. What appears on these cross-coupled pieces here, that's your current state. So it doesn't matter what my current state is because I know 0 NANDed with anything is always 1. That 1 will propagate through here. We'll have 1 NAND 1 is a 0. 0 comes over here. And again, we've got a 1. So we're in a stable configuration. What does that mean, though? That means that Q is 1, Q bar is 0. And that's why we call it S bar, R bar. This is like having active low inputs. To set this device, to set Q high, you have to put a 0 onto the S bit. Conversely, if I wanted to hold, now I need to put in a 1, 1. So let's change this now to a 1, 1. I know that my current state of Q is a 1. So now when I look at this, I've got 1 NAND 1 is a 0. That 0 propagates through. 1 NAND 0 is also a 1. So we're in a stable configuration, and we keep our 1, 0. So with S bar, R bar latches, this is my set state, and this is my hold state. So the difference is with NORs, your hold state is 0, 0. With NANDs, your hold state is 1, 1s. All right, let's also look at the reset state. Reset state, since it's an active low input, you put a 0 on the R pin. All right, let's see what happens. So let's even assume for the moment that we have a current state. Does it affect us? If I put a 1 on S and a 0 on R. Well, if I put a 0 on R bar, it means it doesn't matter. I know that I'm going to get a 1 output. 0 NANDed with anything is always 1. So that 1 will propagate through. I'll have 1 NAND 1. What is that? 0. That 0 will propagate through. I'll have 0 NAND 0, which is still 1. So we're back to a stable configuration. The only thing that's changed here, 0 and 1. If I were to then apply from 1, 0 to a 0, 0, I'd be back in a hold state. So I'd have a reset state, back to a hold state. What binary combination of S and R haven't we tried? 1, 1 was the second state and the fourth state. Oh, excuse me. I miswrote that. I got a little ahead of myself. If I went back to 1, 1. We have actually tried 1, 1 twice for the hold state. If we try 0, 0, that's where things are again going to get interesting. Okay. So if I put a 0, 0 on here, need my little eraser. So let's say that we have a current state, and our current state is a 0. All right. That's our current state. And we change this to be 0, 0. 0 in, 0 in. Well, what do we have? Well, on the output, both will become 1. Because 0 NANDed with anything is always 1. So these 1s will come across, but it won't matter. 0 NANDed with anything is 1. Again, this is what we call a forbidden state. And it's forbidden for 2 reasons. Again, it breaks up the idea that Q and Q bar should always be opposite of one another. But it is a stable configuration. The problem comes when we go from 0, 0 directly to 1, 1. Okay, because right now we have 1 on both Q and Q bar. So if I change S and R at the same time, I know that 1 NAND 1 is always 0. And over here, 1 NAND 1 is always 0. So that brings zeros to the other side. 1 NAND 0 is always 1. And this will continue on for some time. And let's look at that real quick on a NAND latch. So changes. So here's my NAND latch. And you'll notice that right now it's actually in that astable configuration. It just changed. It just launched into a correct configuration. If I try that again, go all the way back to the beginning, because I have 1, 1 here, and both the outputs are 0, that's my forbidden state. Okay? Eventually, though, it does settle into one of the lamps being on. So if I turn one low or the other low, I can always go back to my hold state. But if I ever turn both of them low, that's my forbidden state. Both of them are actually on now. And if I were to change them both at exactly the same time, I just froze time there, and continue, yeah, it doesn't really know what to do for a moment. It will eventually, due to small differences in the silicon level and propagation delays, it'll eventually settle on something. But for a while, it will be astable. So let's go back to that. Okay. So at this point, I think we've seen that astable circuits, they kind of suck. We don't like those. So the question is, how do we avoid astable configurations? Well, I've actually given you a bit of a hint. When I was doing this on the screen, it was actually impossible for me to go directly from 0, 0 to 1, 1 unless I was able to freeze time, basically stop the circuits from propagating. Okay, in order to do it, I had to pause the whole simulation, set them both toggled high, and then resume the simulation to get that astable state. So what I'm going to build now, okay, is a new version. I'm still going to keep my NANDs, my NAND cross-coupled gates. There they are. And I still have Q, and I still have Q bar. But what I'm going to do now is I'm going to gate the input. I'm going to protect that input. Okay? What I'm going to do is I'm going to take this gate right here. I'm going to connect it to something called enable. I've still got an S and an R input. Those should all be NANDs, 4 NANDs. S and an R input. Okay. But what this allows me to do is make sure that I always keep my S and R inputs opposite of one another. So now I have three inputs, S, R, and enable. So in the case of enable being 0, let's look at what happens. Just as a reminder, NAND gates are as follows. Okay, so if I've got a 0 on enable, regardless of the inputs S and R, what am I going to have on these two controls here? If enable is 0, well, 0 NANDed with anything is a 1. So it doesn't really matter what these are. Okay, S bar and R bar will both be 1. Now, remember, 1 on the NAND latch is my hold state. Okay, I have a hold state when I have a 1, 1. So looking at this, when my enable is 0, excuse me, Q is going to be in a hold state. Now, Q bar will also be in its opposite. All right, but we're in a hold state. Once we turn enable 1, all right, 1 NANDed with anything, this effectively turns into an inverter here. Does everybody see why that's the case? So this is basically a controllable inverter or set to 1 circuit. So with this as 1, we have an inverter. So if I put in S here, it goes to the inverter, I'm back to S bar. So I think it's easier to start with NOR gates. Let's just back up a second. It's easy to start with NOR gates. 0, 0 is hold. You put a 1 on S, you set the bit. When you put a 1 on R, you reset the bit. Makes sense logically. But from here on out, we're going to be using NAND gates. Even though it's active low logic, once we start adding control circuitry to this, it goes back to active high logic. Okay, everything here is active high. So if I put in a 0, 0 with this 1, what do I get? Well, I put a 0 here, 1's there. What happens with 0 NAND 1? It's a 1. So I'm effectively still in a hold state. So there's a couple of ways to get into a hold state. Finally, we can get to the other combinations. If I put in enable high, S as 1, R as 0, I end up, again, I'm gating things. So S is going to be, S bar is 0, R bar is 1. So effectively, we've gone into our set state. So that means Q will be 1, Q bar will be 0. If I put in a 0, 1, I will have a 1, 0 on S bar, R bar. So that's my reset state. What happens if I put in a 1, 1? Well, now things get a little tricky. 1 NAND 1 is a 0 on S bar, R bar. And if we look at that, 0, 0 is a forbidden combination. Not good. We don't want that. The whole point was to avoid this, I thought. We do get a 0, 0, which is a forbidden state. So this doesn't actually solve our problem, okay? It does to a certain extent because we can disable the control input here. We can disable it until we're sure that S and R are opposites, but not really beyond that. It doesn't prevent us from actually sending bad data in. So the next iteration of this, because this is a SR latch with control, or with enable. Okay, it doesn't really matter which, but with some kind of control input. Now we want to make sure that we can never get to this state. This is the bad state that we're always trying to avoid. So how can we do that? Well, the simplest way, okay, is we want to make sure that S and R are always opposites of one another. So here's my cross-coupled latch topology. All right, the other inputs are going to go to my gated NAND gates, which do still have that enable input. But what I'm going to do now is I'm just going to take one input and I'm going to invert it. Now, that means that S and R will never be the same. So what we have here, we have S, we have R, which translates into S bar, R bar, okay? Now, normally, this would prevent us from doing two things. It would prevent us from entering the forbidden state, because we can't have 0, 0. What other option will it prevent us from doing? The hold state, which is kind of the point of latches. We want to be able to latch that data in and hold it. It's a memory circuit. If we can't hold the data, what the heck is the point? But, go back here. There are actually two ways to enter the hold state. One option is what we've done all the time. Put 0, 0 on S and R. That's the hold state. The other option is disable the latch. So, here, and by the way, we stop calling it S at this point. We call it, we call it D. This is what we call a D latch. Or, sometimes we call it a transparent latch. So let's take a look at what happens now, because now there's only two inputs. We have enable and we have D. So what do we get? Well, if enable is 0, it doesn't matter what D is. Enable, 0. 0 NAND to anything is always 1. So those will be 1, which means we're effectively in a hold state. So, hold. Once enable is 1, let's look at what happens. If D is 0, what do we have? We have a 0 here, we have a 1 here, and now we've enabled this. So what do we have? 0 NAND 1 is a 1. 1 NAND 1 is a 0. So a 1 on S bar and a 0 on R bar puts us into what kind of a state for this NAND latch? Don't be shy. Don't make me call on somebody. If we have a 0 on R bar, which is what we have, right? I'm sorry, we have a 1 on, no, we have a 0 on R bar and a 1 on S bar. So we have this state right here, 0 on R bar, 1 on S bar. That gives us a reset. Okay, that makes Q be a 0. If we're enabled and we have a 1 on D, that gives us a set state. Those are the only possible ways to do things on a D latch or transparent latch. Another way of looking at this, okay, is, where's my pointer? If this is 0, nothing that happens on D will be reflected on the output Q. However, if enable is 1, anything that appears on D will also appear on Q. Now let me just quickly pull up a D latch and we can just play with it for a moment. There's a lot going on here. Let's start with this one up top. Ignore the 2 lines that are going off to the bottom for a moment. So here I have my D input, and notice anytime I change it, because my enable input, can you see my mouse cursor, by the way? So this is my enable input on the middle, and I'm currently enabled. Any change on D immediately translates to the output, which is kind of fun. If I disable this, any change I make on D doesn't matter, because look at what my S bar and my R bar is doing. They're constantly 1 because 0 NAND anything is 1. So as I go crazy on D, nothing is being reflected on Q until I enable it. And that was an interesting thing. Did everybody just see what just happened when I enabled it? Okay. Right now, I've got Q bar highlighted. If I disable this, I can twiddle D around as much as I want, okay? But nothing changes. What I've done, though, is I've left D high. Normally, when D is high, you'd expect to see Q high as well. So as soon as I enable this, that D translates across to Q, which is kind of fun. So this is the first way to look at a D latch. Okay, it's got an inverter in between S and R. Perfectly reasonable. Now I'm going to give you a hint about the next lab. I'm going to move my D input around here. This is in fact the same circuit. It looks a little different. Okay, here is my enable. Okay, so if I disable this, notice that changing D makes no changes. But as soon as I enable it, everything goes crazy. This is a way to another way to build a D latch. It takes advantage of the fact that a NAND gate can be used as a controllable inverter. If you put a 0 into a NAND gate, it turns into an inverter. So this line is actually going to be the inverted D, okay, which is also the inverted S. So as I disable this, this is a way to build a D latch with only 4 inverters without having to use an inverter, which is extremely handy. All you have to do is bring the enable or the control line to both inputs. The D line goes to the top NAND gate. The output goes to the second NAND gate and to the S bar R bar latch. Okay. This is super handy for lab. Questions so far? Okay. Let's go back to my screen here. So today we talked about a bunch of different latch types. Typically, we don't spend our time drawing out all the NANDs and the NORs. We use block diagrams. Actually, let's start a little bit earlier. So the first thing you might see, this is my NOR latch. Okay, the NOR latch implies S and R. And it gives me a Q and a Q bar output. So to make it real easy, we just say S, R, Q, and Q bar. We actually get even more terse than that. Okay? Because the latches are basic building blocks of so many things, we don't even write Q and Q bar anymore. We just say Q and an out, or we don't even say Q. We just use a line and a line with an active low symbol. That's Q and Q bar. This particular one here still implies that we're building this with NOR latches. To indicate that we're using NAND latches, we would either do something like this to indicate that S and R are active low, or we might say S bar, R bar. This implies NAND latches. Okay, so basic building blocks, NAND latches, NOR latches. From there, we did talk about another kind of latch, latches that have control. Okay, this control might also be enable. You would choose one or the other. Now, because these are active high inputs, S and R, okay, we don't use bubbles except for the Q bar output. This is an SR latch with control. Finally, we ended with D latches. So these are the shorthands. If you see this symbol, that means that we're talking about one of the types of latches we talked about today, either the transparent D latch, the SR latch with enable, the SR NAND latch, the SR NOR latch. Okay, and in fact, using this tool, I'm gonna go a little off script here for a second. I'm gonna go new circuit, or let's save this. New circuit here. I believe that inside this tool package, they provide you with all of these things. Oh, they do. They provide you with all of them. There's SR. There's S bar, R bar. There's a D flip-flop. We won't get to D flip-flops yet. That's a little different. Okay? So I've got all my latches available to me. This one, see, this is a little bit of a pet peeve of mine. So this says S bar and it has the bubble. So is that like a double negative? The short answer is you ask the author of the question, or you ask the author of the thing, or you just test it out. And it's easy enough to test this out. Let's do that right now and see exactly what they mean. We can build that right now. I'm going to take two logic inputs here, connect those up, take two logic outputs. Where are they? There, they are lamps. And drag them into place. I find this extremely helpful for visualizing what's going on in different circuit types. So just clicking on two endpoints will connect them together. There we go. And we can start simulating. And notice right away, what do I have? I have too high. That's a forbidden state. So this is saying 0, 0 is a forbidden state. So if I go now to just a single one, I didn't go from a forbidden to a hold. So I've gone into a reset state because we're in active low logic. I've put a 0 on R. That implies reset. And then I go to a hold and I go to a reset. So we actually have S and R latches available to us. So I'd like to try something now with S and R latches, but I'm actually going to, instead of using S bar, R bar latches, NOR latches, I want to use a full SR latch like this, but this doesn't have a control input. So if I go like this and simulate this, now I've got my set and my reset, and 0, 0 is my hold. So to actually do the next step, I'm going to have to add a little bit of circuitry, I think, unless they have. Doesn't look like they do. Well, darn. It's easy enough to build, though. Oh no, because I need. Oh, it's not easy to build with this. That's unfortunate. Let's go back to my old circuit then. Let's go to my D latch. Discard those changes. All right, I've got two D latches here right now. And what I'm going to do is I'm going to disconnect them from each other. And I'm going to use them. Actually, let me just recreate both of these here. Take this guy there as such. Take the, oh, you know what? This is actually going to take a little bit longer than I think we want to spend. Let's draw it out first so that we have a plan for where we're going. I'm going to take an SR latch with control, and I'm going to hook it up to another SR latch with control. Now, the way I'm going to hook it up is I'm going to hook up Q and Q bar to S and R. Furthermore, I am going to put together an inverter here. So I've effectively turned this first SR latch with control into a D latch, or a transparent latch. And in fact, this second SR latch with control is also a D latch, even though I didn't use an inverter. Why is that the case? What does it mean to turn an SR latch with control into a transparent latch? Well, but how do you turn an SR latch into a D latch? What do you have to do to S and R? Yeah, you have to hook them up so that they're always opposite. Now, if I've set this up right now so that S and R are always opposite here, that means that for my Q and Q bar, I will never have a forbidden state. So they are already inverted. All right, here's where the magic comes in. This control signal here. So let's do it in a different color, just so we can see what's happening. I'm going to take that control signal and bring it through an inverter. Now, this is the start of some really cool stuff. This configuration is what's known as a master-slave flip-flop. Master-slave flip-flops are significantly more useful than latches. We saw in the previous example here that if I hook this up like this and run this, as long as I am enabled, any perturbation in the D input will be reflected on the output. Oftentimes we don't want that. We want it to only happen once. We only want to deal with it once. So with that said, I am in fact going to build this. I don't think it's going to take that much longer to build. Let's quickly just move my SR latch with control over. Okay. We can even leave those lights in, I think, and it won't hurt us too much. Now instead of, oh yeah, you'll still have to go to ground there. But now I'm going to put in my next D latch, or transparent latch here, like so. This fills up almost my whole page, but I think we can make it work. So what I'm going to do is, again, I'm going to hook up, connect. Oh, do I have to stop? There we go. So I've hooked up my Q and Q bar outputs together. No, I haven't. What did I do wrong? Yeah, I've got to share my enable here. So this is actually my enable, and I'm going to hook those two up together. So now I have two things connected together, but actually I wanted to do that through an inverter. So let me throw one inverter down here. Okay. So connect up my inverter to my enable signal. My enable signal goes to both of these. Okay, and we begin simulating. Right now, I am enabling this guy. So as I... Oh, what did I... Oh, you have to go there. Stop. Delay game, 5 yards. Connected. So, with this first flip-flop enabled, it's transparent. You can see that everything I do on the D input extends out. What do you notice about the inputs on the far end as I'm sitting here twiddling this like a crazy person? Yeah, that enable over here is inverted. Okay, so there I can actually see the whole thing. It's inverted. So this D latch is not transparent. Okay? So whatever is happening on the output Q is stuck there. If I now turn this around, notice that nothing I do here is reflecting on the output. Okay, so how on earth do we actually cause a change here? Well, putting a 1 here and twiddling my enable line allows us to capture. So let me actually do the following. I'm going to replace this D input, actually I'm going to replace the clock input, pause, with a toggling source. So this is going to actually toggle back and forth, 0, 1, 0, 1. And what I'm going to do is I'm going to click the D input like a mad person. Okay? Notice that as long as this is high, any change I make here on the D input is reflected. So as soon as that goes high, well, I'm going a little bit too fast for this right now. How to make that work? So as I make those changes, I need to speed up my simulation time here by quite a bit. Yeah. Okay. So as soon as I make a change, notice that a few cycles after, or really 1 cycle after I make a change here, the first Q triggers the second Q a cycle later. High, high, low, low. What we typically call this input, and we're going to continue this for the next couple of classes, so don't fret if you haven't figured it out yet, or it isn't apparent yet. It's what we call a clock source. I would encourage you to try to build this circuit, not least because it's part of your lab. Okay? This is a master-slave flip-flop. First, this, oops, not on the right one. First, this SR latch with control has to get its output to appear. Then, control is transferred, okay, to the second latch. We typically refer to this as edge triggered. Edge triggered means it only updates its final output on an edge. You will only ever see it happen on an edge. You will never see it like a transparent latch, level sensitive. So all the things we talked about for the first part of class today, these latches, are all level sensitive. They're sensitive to the level on your control or on your enable. By pinning 2 of them together, we actually end up getting an edge-triggered device. And there are problems with this that hopefully I'll be able to show you on a simulation next class, okay? 2 things. I meant to stop early. As you leave, you can collect your exam. And I will be posting via email all of the homework for Chapter 5 today via email, okay? It is not going to be due for a while, but I want you to start working on it now, see what you can try. I'm going to give it to you all in one lump sum, because I did not assign any for Chapter 4, did I? No, I did not. Okay. So, come up and just give me your last name, because there are going to be a lot of people asking for exams.